Okay, good morning, everybody. And last class, we finished talking about blood, liquid substance that makes its way all around the body. Now we need to talk about how that liquid makes its way around. And in order to do so, we first of all got to talk about the heart, which is the pump that drives the blood around the body. And then we've got to talk also about the circulatory system that the blood makes its way through. Today, we're just going to be talking about the heart. There's plenty to talk about when we discuss this incredible muscle that lies in the center of our thorax. And we all think we know something about the heart, but it's actually a very complex and very carefully controlled organ. In the old days, actually, they used to think we thought with our hearts, which is quite a strange thing to realize how the cultural change can take place, that we now assume we think with our heads. They used to think we thought with our hearts. Now we still always talk about feeling with our hearts. And indeed, if you think about it, we do seem to lodge feeling in our chests. That has nothing to do really with the actual structure of the heart or anything. But the heart definitely responds to emotion. It responds to emotional cues that are sent by the autonomic nervous system. And the heart is, the nervous system of the heart is actually controlled by the autonomic nervous system. The heartbeat can be sped up, slowed down, etc., in response to circumstance, and especially in response to emotion. Okay, so we're going to talk about some of the structures of the heart and some of its functions. The first thing is that the heart is a pump. It's a very elaborate pump. In fact, it has two systems which operate in unison. It has two circulatory systems that it controls, and it is the place where the blood is actually shared between those systems and distributed around the body. So first of all, it's a pump. Like any pump, it's got valves and all sorts of things to direct the flow of the fluid, the blood that passes through it. And in the heart itself and in the body in general, the blood is conducted through arteries, which are muscular vessels invested with a muscle that actually contracts, can contract, and then the system of veins. The arteries are those vessels which lead from the heart and away. Veins are those vessels which bring blood to the heart. The arteries, we'll learn a lot more about the circulatory system later. So I'm just mentioning. The arteries that leave the heart, for example, subdivide. They divide and divide and divide into smaller and smaller and smaller vessels, until in the end, the vessels are so fine, they barely allow the passage of individual red blood cells, which squeeze their way through. Blood is gathered in the veins and is moved back to the heart through mechanisms that we'll talk about later. So we know blood is a transport mechanism. First of all, it transports oxygen and nutrients to the cells, and it carries waste products from those cells to the organs of excretion. What you may not know, or may not be clear to you yet, is that there's in fact a parallel circulatory system, which is called the lymphatic system. And we'll learn when we talk about circulatory systems, we'll learn how that figures into the whole system. For today, we're just going to be concentrating on the structure and the function of the pump itself. So here you can see the circulatory system, an elaborate system of arteries and veins, arteries away from the heart, veins towards the heart. But it's this that we're going to be concentrating on today, just on the structure of the heart. We'll return to all of this later. So here's what I mean by saying that the heart is a double system. If we look at the heart situated in the thorax, here's what it looks like. It slants towards the left and occupies more of the left-hand side of the body than the right. What you see here on the outside, that is one of the great muscular contraction chambers of the pump. These are the ventricles below. Up here, you can see this is the upper chamber of one of the upper chambers of the heart, called the atrium. You'll sometimes see it referred to as the auricle, A-U-R-I-C-L-E, but the proper name is the atrium. So there's one there. But you'll see these giant vessels, some of them leading to the heart. They've colored them blue, although venous blood, I remind you, whatever your book says, the venous blood is not blue. It is darker red in color, but it is not blue. Deoxygenated blood acquires a darker tone to it than oxygenated blood. So you can see here that there are vessels which are running to the lungs. These are the lungs here on either side. The lungs, obviously, we are bringing in oxygen the whole time. We're filling the lungs with air and to extract the oxygen, and also to dump our carbon dioxide so that we can breathe it out. There is a circulatory system from the heart to and from the lungs. So that is circulatory system number one. The vessels leaving the heart go to the lungs, or the pulmonary arteries. And the vessels coming back from the lungs to the heart are the pulmonary veins. Then, apart from that lung circulatory system, which is taking deoxygenated blood, oxygenating it, dumping its carbon dioxide, then returning to the heart. It is returned to the heart so that it can be sent out in oxygenated form to the rest of the body. And it is actually sent through these they're called the great vessels. And this is one of them here. This is the aorta. You can see it coming back down here underneath. There are others as well. There are other large vessels which leave the heart, especially to supply the head. That blood goes out to the body through those great vessels. It then returns, and it returns here through this vessel here. We'll see later on exactly how it happens. This is a vena cava. So this is a vein leading back to the heart. These are arteries leading away. So that is the second circulatory system. It's the circulatory system which goes through the rest of the body. We have a lung circulatory system, and then we have a circulatory system through the rest of the body, and then sending blood and returning blood to the heart. So this is basically what you see if you were to open somebody's chest and look at their heart. This is more or less how it lies, but of course it's hiding all sorts of structures within which reveal its functioning. Let me see if there's anything I need to take it. Yeah, I just want to emphasize something here that is a little bit confusing. In the systemic system, the system which goes to the body, the arteries carry oxygen-rich blood. And an artery, by definition, is a vessel which leaves the heart to go somewhere else. So this is an artery here called the aorta, carrying oxygenated blood to the rest of the body. But in the pulmonary system, the artery here carries deoxygenated blood because it's sending deoxygenated blood to the lungs to dump the carbon dioxide and to take up oxygen. So the artery in this case is carrying deoxygenated blood, and the pulmonary vein carries oxygenated blood back to the heart, which is then pumped out through the arteries. So the heart, it's about the size of a closed fist, weighs about a pound under normal circumstances. And it beats from very, very early on in your life in the womb as an embryo. It starts beating, and it carries on beating for the rest of your life. And human beings, we tend to regard the cessation of a heartbeat, the final cessation of a heartbeat, as being a sign of death. So it goes from very, very early on, the fetus, up till the point of death. And it's located in the thoracic cavity. So this is your thorax, so that is the thoracic cavity. Here's a heart taken out, dissected out. And here you can see, first of all, there are the great chambers, the really heavy muscular chambers, which pump blood to the lungs on the one side and to the body on the other side. And here, that there is an atrium. There on the other side is the other atrium. Here's the aorta going off here, and here returning blood to the heart are the vena cava. I just want to point out something. Oh, sorry. Let me just point out one thing to you. Notice that the blood has its own vessels. It has its own arteries and veins, and those are the vessels which supply the muscle of the heart with oxygen. The muscle of the heart requires a rich supply of oxygen. It is extremely active, extremely metabolically active. So it needs a constant supply of oxygen-rich blood, and that it gets through these vessels which run down and penetrate and supply the muscles of the heart. Those are the coronary arteries. And remember that word, coronary artery, because when we talk about diseases of the heart, this is one of the sources of problems. Is blockage of those coronary arteries can lead to severe problems. Okay, so the heart itself is surrounded by a double membrane, and this is a synovial membrane. And if you don't remember what that is, you need to go back to our discussion of tissues and membranes. A synovial membrane is one which a double membrane, and it secretes a fluid in between. And this is the pericardium, which surrounds the heart. It's a protective, connective tissue synovial membrane, which acts as a kind of a buffer in a way, because it's fluid filled and is protective of the heart. Here you can see leaving here the aorta there, and that aorta is going to find is actually actually joins in, blood is pumped from the left ventricle into the aorta. This is the vena cava. There are two vena cavae. One is called the superior vena cava. It drains blood from the upper part of the body. The other is the inferior vena cava, which is not shown here, which comes up here and drains the rest of the body, sends deoxygenated blood to the heart. On either side, the lungs, and below the heart is the diaphragm, which defines this basically defines the borders of the thoracic cavity. The diaphragm, and then the ribs containing the lungs and the heart. Now, the importance of the heart can't be overemphasized, because we absolutely critically require a constant circulation of oxygen-rich blood. This is particularly true of the brain. It does apply to all other organs as well, but some other organs have a longer tolerance of low oxygen levels than the brain does. After 4 to 5 minutes without blood flow, without oxygenated blood reaching the nerve cells of the brain cells begin to die, and they are irreversibly damaged. You tell whether somebody's got a heartbeat from various ways. Everybody should do a first aid CPR course and learn how to quickly assess whether there is a healthy heartbeat which is sending oxygenated blood to the body. There are various ways for taking pulse points, for instance. If you put your fingers here, kind of against your Adam's apple there, you'll feel a pulse. That's the carotid pulse. You're feeling your carotid artery, blood rich in oxygen going to your brain. But the heartbeat can also be heard through a stethoscope. There are various other pulse points, your wrist, for example, where you can take a pulse. If the assessment is made that the heart has stopped beating, then heartbeat can be restored by various means if action is taken quickly. And this is the importance of doing cardiopulmonary resuscitation. There are two aspects to it, to this critical situation. First of all, is if there is no heartbeat, the person may still be breathing, but they will not be sending oxygen-rich blood to their body. And situation number two is where there's no heartbeat and they are not breathing. So cardiopulmonary resuscitation, it takes care of both of those. And in CPR, you learn to apply a mechanical pressure to the heart, which passively pumps blood through the heart. The heart, we're going to find out, consists of these 4 chambers with valves running, controlling the flow of blood through the heart and into the vessels. And if you passively compress and allow the heart to relax, blood will still be pulsed through the heart and then through the vessels sufficiently that you can supply enough blood to the brain, especially, to keep it alive until some other means of getting the heart going again can be resorted to. Everybody should learn CPR. The current standard is that you give 30 beats of the heart to 2 breaths. It used to be 15 to 1, now it's 30 to 2. And that is sufficient, done efficiently, that is sufficient to keep people alive. But I must tell you that the long-term outcome of CPR in terms of numbers is not actually that high. But nonetheless, it's worth trying because some people do survive. So the heart is a hollow, very, very muscular double pump. I've explained to you that the pericardium is a synovial membrane around the outside that is filled with fluid called the pericardial fluid. The muscle itself we call the myocardium. So myo always means muscle. So the myocardium is the cardiac muscle itself. But the muscle, the whole of the inside of the heart is lined with another membrane called the endocardium. And the endocardium is a highly specialized membrane. It's very similar to the membrane which coats the rest of the blood vessels of the body. And it is of particular interest at the moment because it appears that COVID-19 virus, the virus that causes COVID-19, in some cases attacks the endocardium and causes problems, especially it causes roughening of the endocardium and it causes platelets to settle and slow down against the endocardium and start clotting. So that is one problem associated with COVID-19. Okay, so here's the structure. Yes, please, you are to learn it. And I've said at the end, please go to the end of your chapter. There's a diagram of the heart. You are pleased to learn the external structures and then some of the internal structures as well. First of all, the most obvious part of the heart are the ventricles. Here's the left ventricle here. It's larger than the right ventricle there. Here is the atrium. Sometimes you will see some textbooks refer to it as the auricle, but we'll refer to it as the atrium. Here's one here, and then there's another small one on the other side here. Here are coronary arteries here. And then, of course, this is a circulatory system. The heart has its own circulatory system, just like any part of the body. Blood is sent in the arteries, and it is returned to the heart through the coronary veins. The great vessels entering and leaving the heart, first of all, the easiest one to recognize is the aorta. The aorta here is curling around and down, plunging down to the rest of the body, but it gives off 3 major arteries here to supply the upper part of the body and the brain. So the blood is sent off to the body and it is returned to the heart through the vena cava. Here's the inferior vena cava here. Here is the superior vena cava there. And these are returning blood to the heart. They're actually returning it to this atrium here. So this vessel here is the pulmonary vein. Now in this diagram here, they've colored the pulmonary veins red because they are carrying oxygenated blood. Remember that the terminology is swapped in the pulmonary system because these are veins, they're running back to the heart, but they're carrying oxygen-rich blood. The lungs, the blood running to the lungs, which is deoxygenated, is carried by this artery here, the pulmonary, and this is the right pulmonary, and by this one here, the left pulmonary. Blood is then returned to the heart through the pulmonary veins, there, the right pulmonary veins, and here, the left pulmonary veins. We'll find out what happens to that blood in a little while. We'll find out once we open the heart, we'll see exactly how it circulates. So please make sure that you know this diagram and understand the different parts. So here, let's open up the heart and have a look. Again, we're seeing exactly the same vessels and everything. Here are the pulmonary veins, pulmonary artery. Here is the superior vena cava, inferior vena cava, and here is the aorta. How on earth does all of this fit together? Well, first of all, blood has got to return to the heart, and it is returned deoxygenated. So it's got to be oxygenated. So the first thing that the heart does is it sends deoxygenated blood off to the lungs. So the blood comes into this is the atrium here. The blood comes into the atrium through the vena cava. They drop the deoxygenated blood into this chamber here. When this chamber contracts, it sends all the blood here to the right ventricle. And when this right ventricle contracts, it sends the blood off through the pulmonary arteries here, off to the lungs. So there's our first circulatory system. Here's why we say it's a double pump, because the whole of this side is a pump on its own. It's receiving the blood from the body here into the atrium. When this atrium contracts, there is a huge valve here that allows the blood to pass into the ventricle. But when the ventricle contracts, this valve here slams shut. And the blood in it can't return to the atrium now. If this contracts, it can't return to the atrium. It's only got one way to go, and that is out through these arteries. There are huge valves also here at the beginning of this pulmonary artery to stop the blood from flowing back at all. So the blood is a one-way flow from the body to the atrium, to the ventricle, out to the pulmonary arteries. In the lungs, those arteries divide and divide and divide and divide and divide and subdivide into millions of capillaries, which surround the little cells of the lungs, which are inflating and deflating as we breathe. And the capillary walls are so fine that gases can pass through them really easily. And so as the blood, this deoxygenated blood, passes through those capillaries, it dumps its carbon dioxide and it picks up oxygen on the hemoglobin. And that blood then is gathered up again and is returned to the heart through the pulmonary veins. And here they are here. They are huge vessels, and they enter the left atrium, which is here. So those come now into the left atrium. The same thing happens. This atrium is contractile. It contracts and it sends all that blood to the left ventricle here. Again, there's a giant valve. It's called the bicuspid or the mitral valve. And when this huge ventricle, very thick-walled ventricle, contracts, it sends, with tremendous force, by the way, it slams this valve closed and it sends all the blood out through the aorta, off there and out to the rest of the body. This ventricle contracts sufficiently hard, powerfully, that it can actually send a jet of blood about 30 foot from the heart. The blood leaves under tremendous pressure to go through the rest, because it has to make its way all the way through to the rest of the body. So that is the basic circulatory system. Let's do it again. Blood returns to the heart through the vena cava. It enters here into the right atrium. The right atrium contracts and it sends the blood through this, which is called the tricuspid valve. We'll see why in a minute. It's called the tricuspid valve, and it sends it into the ventricle. When that right ventricle, when that contracts, this valve slams shut, and these valves open to allow the blood to pass into the pulmonary artery, and the blood is sent out to the lungs. When it goes to the lungs, it gets oxygenated and it loses its carbon dioxide. And the oxygen-rich blood is then returned to the heart through the pulmonary veins, which are here. And the pulmonary veins enter the left atrium, which is here. The left atrium contracts and it sends the blood through this valve, huge valve here, called the mitral or bicuspid valve, and into the ventricle. The ventricle contracts, and this valve here, the mitral valve, slams shut, and all the blood is sent instead through the aorta to the rest of the body. This is the lub-dub, 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 lub-dub. When you hear lub-dub, lub-dub, what you're actually hearing is the sound of these valves slamming shut under the different pulses of the body as the atria and the ventricles contract. So this heart contraction is actually a really complex thing, and we'll discuss exactly how it happens in a minute. This is just a view of these valves. It's as if we took, here's the heart again, right atrium, right ventricle, left atrium, left ventricle. Here are the great vessels entering and leaving. What they've done is they've cut the heart, this heart in that plane there, just above. They've gone through the atria, and you're looking down on the heart now so that you can see the structure of these valves. They're huge. This is the tricuspid valve, this side here, and you can see why it says tricuspid. Tricuspid means 3 parts, 1, 2, 3. There are these 3 parts to the valve. This is very tough connective tissue. The action of the valve is essentially a passive action. It's not being pulled open by muscles. It is being opened and shut by hydraulic pressure. And the hydraulic pressure is the pressure supplied by contraction of the atrium and of the ventricle. The same thing is true of the vessels, the great vessels entering and leaving. They have their own valve system to ensure a one-way flow of blood under the pressure, under the action of the heart. And here, for example, here is the pulmonary valve there, which is here. That's in the vessel, that's the pulmonary artery going off to the lungs. So, and you can see that they're called semilunars because they look like little half moons. Same here, this is the aortic valve, which is there. There it is there. And so this whole system the pressure, the activity and pressure is produced by this very powerful muscle contractions, especially of the ventricles. The rest of the motion of the blood is largely passive, and it is guided by these huge valves which prevent blood from moving in the wrong direction, essentially. The tricuspid stops it from moving back into the atrium here. The bicuspid stops it from moving back here. Semilunars keep it moving in the correct direction and down the vessels. Semilunars here prevent it from flowing back. Same here in the aorta. They keep it moving this direction through the aorta. They stop it from flowing back. So those are the valves of the vessels. These are the valves which lie between the atrium and the ventricle. So they're often called the atrioventricular valves. The atrioventricular valve, it's easy to remember. Atrioventricular, atrium, ventricle. And they're the valves that lie between the atrium and the ventricle. Here they are summarized for you and telling you exactly which flow, how they govern the flow between the different chambers of the heart. So in summary, actually, if you break it down like this, it's quite easy to remember. And that is that this side of the heart, the right-hand side of the heart, drives that pulmonary circulation. The right-hand side of the heart receives deoxygenated blood, sends it to the lungs, and it is then received back in its oxygenated form by the left-hand side of the heart. And the left-hand side of the heart is the part that drives the systemic circulation. That is the circulation through the rest of the body. And again, the heart sounds, if you listen to them, especially if you listen through a stethoscope, you will hear classically there's lub, dup, lub, dup, lub, dup. The lub is when the ventricle contracts, and the sound is made by the slamming shut of the tricuspid and the bicuspid valves. The ventricles essentially contract together, and they close those two great valves to stop flow into the atria. The dup sound is when the ventricle relaxes, and that is the opening of, closing of the aortic and the pulmonary veins, valves rather, to stop blood flowing back into the ventricles. So that lub dup are the different valves slamming shut under hydraulic pressure, either from the chambers themselves or from blood in the vessels. So here, this shows you exactly how these veins work. How these valves work, and that it is essentially a passive. It's the mechanical structure of the valves that forces them to close. If blood flowing through the valve in the open position, and if blood attempts to flow back, then the leaves of the valve, whatever kind of valve it is, get pushed together and the valve shuts. These are extremely strong structures, and especially the atrioventricular valves here are anchored by very, very strong connective tissues to the walls of the heart. The semilunars are not anchored in the same way. So make sure, please, that you understand, and understand these different valves, tricuspid, bicuspid, or mitral, and then these semilunars that govern the passage of blood in the vessels themselves, stopping blood from falling back into the heart once it's entered them. So you can take your own heart rate quite easily. If you take your pulse, just take your fingers, put them onto the side of your wrist, just below your thumb, and you should be able to find your pulse. You can feel it beating, tuck, 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 tuck. And the normal adult resting rate is between 60 and 100 beats per minute. If it's less than 60, that is referred to as bradycardia. Bradycardia is not necessarily a sign of anything wrong. Some people just naturally have a slower heart rate, but people who are extremely athletic and very fit, their heart rate is usually lower as well. More than 100 beats per minute is referred to as tachycardia, and tachycardia is completely normal if you are exercising, for example, even moderate exercise, just walking or something, to push your heart rate over 100 beats per minute. But constant tachycardia, even in the resting conditions, is often a sign that there is something wrong. Can be in response to all sorts of things, can be in response to other disease processes or to heart disease itself. What is really important is the volume of blood that your heart is pumping out. And that is you work that out by simple math. If we can find out what the stroke volume is, which is not actually that easily done, but it can be determined in a medical setting. And then you take the stroke volume and you multiply it by the heart rate, you get the volume pumped per minute. And the normal is actually a really big amount, is 4.8 liters, 4,800 milliliters, 4.8 liters of blood per minute, on average, are pumped by the heart. That increases prodigiously if you're exercising, because there are various things that can happen. Both the stroke volume and the heart rate can be increased by exercise. So the stroke volume and the heart rate are both increased by exercise. So the volume per minute will go up with exercise or excitement, anything that increases the heart rate. This is one of the great advantages of exercise, of regular good exercise that raises the heartbeat, is that you actually improve your stroke volume. You improve the efficiency of the contractions of the heart. So your volume per minute increases even in the absence of a high heartbeat. So the contraction of the heart is a complex phenomenon. You may remember that I told you about cardiac muscle cells. Cardiac muscle cells have a structure. They're very like striated muscles in some ways, because you can see striations on the cardiac muscle cells. But the cardiac muscle cells connect with one another. The cardiac muscle fibers actually have connections between the fibers. And the reason for that is that the muscle cells have an inherent excitability. They generate their own action potential, and they contract and relax. They contract and relax. And that contraction is transmitted through all the connected cardiac cells. So if you grew them in Petri dish, which you can do, you'd see clumps of them contracting together. If you put them all together, you make a heart out of all of that muscle tissue, and you just left it, well, it would just be twitching all over. It would be twitching chaotically. Its contraction is inherent, but the beat, the coordination of all of those contractions into useful contractions, is the responsibility of a nerve apparatus inside the heart itself. And this is referred to as the pacemaker, because what it's doing, it is regularly sending out pulses, nerve impulses, action potentials, which get all of the muscle fibers of the heart to beat in a coordinated fashion. First the atria and then the ventricles. Then the atria, then the ventricles, and the atria, then the ventricles. And here is the pacemaker system. First of all, there are two big collections of nerves here, where the controlling nerve impulses are generated. They're generated here, and there's coordination between the two. This is called the sinoatrial node. It largely governs the contraction of the atria. This is the atrioventricular node, and this largely governs the contraction of the ventricles. These nodes here have finer nerve fibers which radiate out to conduct the nerve impulse. And the atrioventricular conducts largely through these. This here is called the bundle of His. And it subdivides into smaller, and then radiates out all through all of the ventricle here. And these are called the Purkinje fibers. So you can visualize that a nerve impulse is generated here and is amplified really here by the atrioventricular. It spreads, it runs down here and all the way through here, and wherever it goes, it causes the heart muscle fibers to contract. So first of all, we have a radiation through the atria contract. It runs down through here, is amplified by the atrioventricular node, runs through here, down and around, and you'll see the ventricles contracting as those nerve impulses pass through the ventricles. This, by the way, the pacemaker is under the overall control of the autonomous nervous system, which is controlling the rate at which the impulses are made. They have an inherent pulsing. Okay, you can extract a living heart and observe it beating under the action of the inbuilt pulse of the pacemaker nodes. But the heartbeat can be raised and slowed by activity, by instructions from the autonomous nervous system under various means that we'll talk about when we talk about the endocrine system. These can be increased, for example, by their receiving hormonal instructions to increase the heart rate. For example, if you get a fright, that is exactly what happens. Adrenaline is sent to your heart, and it instructs the sinoatrial and the atrioventricular nodes to increase the rate at which they send their impulses out to get the heart to beat, so the heart will beat faster. So it begins, the nerve impulse begins here, sinoatrial, goes to the atrioventricular node, and then down and around, out through the rest of the heart like this. And when you go and have your medical checkups, very often they will do an EKG or an ECG. It's the same thing, electrocardiogram. EKG is just the German letters. Electrocardiogram, and they put electrodes all over your body. And what they are doing is they are measuring the electrical impulses generated during the heartbeat. That is, this is what they are following. They're following this lub-dub, lub-dub, lub-dub. And this, obviously, you know, you've seen this 1,000 times, this little diagram of a heart contraction. In actual fact, this is the atrial contraction here, and this is the ventricular contraction. But what you're looking at is, when you look at an ECG, is not the actual contraction itself. You're looking at the electrical impulses which produce the contractions. That's what they're measuring. Contraction is referred to as systole. That is the contractive phase of the heartbeat. Diastole is the relaxation part. So systole, diastole, systole, diastole, systole, diastole. when you have, you'll know probably that when you have your blood pressure taken, sorry, I'll come back here. When you have your blood pressure taken, they take two measures. They take one measure, which is the pressure under the force when the heart is contracting, the pressure is usually higher. And then diastole is the relaxation pressure. That's an inherent pressure throughout your circulatory system when the heart is not in contraction. So we measure blood pressure as systolic during contraction, diastolic when the heart is in relaxation. So when they generate that ECG wave, this is what it means. You don't need to know all the details, but I'll just show you what applies. First of all, there's a little peak here. This is the generation of the sinoatrial wave there. So that's the electrical wave there, the nerve impulse. Now this ventricular depolarization begins. It's coordinated between these two. Now the ventricular pacemaker causes a wave, and that radiates out through all of the ventricular muscles, and it causes a ventricular contraction. This word depolarization simply refers to the generation of the nerve impulse. That is what the depolarization means. Atrial depolarization, nerve impulses through the atria. Ventricular depolarization, nerve impulses through the ventricles to cause their contraction. And then after that, the heart goes into a relaxation period, kind of a recovery period before the next contraction is generated by the pacemakers. Okay, we do need to talk a little bit about heart disease because there are several diseases of the heart. Heart disease is still the leading cause of death in the United States. Largely due to coronary heart disease, that is disease associated with the circulatory system of the heart itself. And that is disease of those arteries that supply the heart muscle with oxygen and obviously with nutrients and everything as well. Those coronary arteries, the coronary vessels, are extremely small, very thin, and they are easily occluded. They're easily blocked. Under normal circumstances, they stay open perfectly fine. But there are certain risk factors associated with them which you can acquire. The first, unfortunately, you can do very little about, and that is that there is a genetic component to heart disease. It tends to run in families. But there are a lot of other things which contribute to poor coronary artery health. And I'd say still probably one of the most important is smoking. Smoking is extremely dangerous for the heart. And smokers carry a much higher risk of coronary artery disease than other people. Equal or probably slightly below smoking, I would say, is the impact of diet, because high lipid diets tend to predispose to coronary artery disease for a reason I'll describe in a minute. Next is stress. If the heart is kept under the stress from the autonomic nervous system, it engenders disease. You can think of it actually of the heart essentially becoming overworked. But equally bad is inactivity. Lack of exercise. If the heart is never pushed slightly, the heart needs to be pushed slightly continuously to maintain heart health. It is very, very good, at least once a day, to raise the heart rate for at least a half an hour. This has been conclusively shown in all sorts of studies to be very, very good for heart health. Inactivity is a high risk factor for coronary artery disease. And the next is obesity. Overweight puts a huge strain on the heart, but it also places a person at risk of coronary artery disease. all of these things are lifestyle choices apart from genetics. And all of them, these risk factors can be ameliorated by changes in lifestyle. And the vast majority of heart disease is avoidable. Eventually, your heart will eventually stop. That is true. But you don't want it to stop before its time or before yours. And all of these things need to be considered. And above all, I think that the most important thing of all is this one here. And that is to get exercise. Exercise, not only because it exercises the heart, but because it means that you probably be able to keep your weight under control much better. It de-stresses you. And if you are keen on exercise, you're very unlikely to be smoking. Your genetics you can do very little about, but you can, genetics predisposes people to heart disease. It makes them much more susceptible to these risk factors. So even if you have a genetic predisposition to heart disease, you can do a lot about it by modifying your lifestyle. Now, this issue of looking at the levels of lipids, of oils and fats in the blood is a somewhat controversial one. There are many cardiac scientists will tell you that this is a very, very important aspect of heart health, is looking at blood cholesterol levels and triglycerides. Triglycerides are fats in circulation in the blood. Blood cholesterol levels are a reflection of your overall lipid intake, let's say. And the danger of cholesterol is that it tends to form plaques, which are coatings inside blood vessels. And this becomes especially dangerous. It can happen in any vessel, but it becomes extremely dangerous in the coronary arteries because it now begins to narrow the coronary arteries. These narrowings are actually layers of substance called lipoproteins. And they are, when you go and have your cholesterol, it's commonly termed cholesterol. And when you go to have your checkups, they will usually look at your total cholesterol levels, and they will divide it into two. They will divide it into low density lipoprotein, LDL, which is referred to as bad cholesterol. It is extremely likely to form plaques in blood vessels. And desirable, you have to have lipoproteins. It's an essential part of your diet. But the desirable levels in blood should be less than 100 milligrams per deciliter. That's per 100 mil. So high density lipoproteins are referred to as good cholesterol. And the reason that they're referred to as good is it appears that the high density lipoproteins are protective of blood vessel walls. They prevent the deposition of the low density lipoproteins. But nonetheless, your total cholesterol should be less than 200 milligrams per deciliter. So you won't necessarily remember this one there. Total cholesterol should be less than 200 milligrams per deciliter. But when you go for your next checkup, you can refer back to this to see what desirable levels are. Then another measure that is taken is that of triglycerides, which are fats, which enter into circulation as part of your digestive process, but they should be less than 150 milligrams per deciliter. So these kind of established healthy levels for these things. Many, many, many of us will exceed these at one time or another. We can exceed them once or twice a week, depending on our diet, et cetera, et cetera. But the important thing is long term. If you carry a high burden of these long term, then you're predisposing yourself to damage to the vessels, especially of the heart. Keys for a healthy heart: stop smoking, lower your blood pressure, watch your alcohol use, keep a healthy weight. Your BMI should be between 18 and 24.9. Get regular exercise, raising the heartbeat at least 30 minutes a day. And then in your diet, lower intake of sugars, fats, salt, which tends to raise blood pressure. And I would also add, increase your fiber, increase the amount of fiber that you take in. For this reason, it's a little bit obscure, but fiber, high intake of fiber appears to improve your gut microbiota. It improves the bacteria in your gut. And this is another link, which we won't talk about, but it's just being established that there is a link between healthy gut microflora, bacteria and everything, and healthy hearts. With age, your heart will start to decrease its efficiency as heart muscle fibers get replaced by fibrous tissue. The heart valves tend to work less efficiently. Cardiac output decreases. And these are all amplified if, with aging, the person becomes inactive. People can maintain extremely healthy hearts until a very old age if they regularly exercise. So that is something to bear in mind. Here are some diseases of the heart. That complex beat system of the pacemaker can go wrong. You can acquire damage to the pacemaker through disease, or else just with aging, or for reasons that are unknown. And that leads to arrhythmias. There can be arrhythmias of the atria. That's one thing. Atrial arrhythmias are better tolerated than ventricular. Ventricular arrhythmias are very often fatal, and they arise because this coordination of the beat is lost, and the ventricle goes into chaotic twitching instead of a strong beat to drive the blood. Sometimes valves do not shut properly. One leaf of the valve, for example, may lag behind another and allow some leakage of blood during the heartbeat. This can often be heard as a whooshing sound, which they will identify as a heart murmur. Sometimes these murmurs are just benign. They're quite common, and they may have no impact whatsoever. But severe murmurs are indicative of failure of part of the valve, and that can be extremely dangerous. One of the common ones is called mitral valve prolapse, and that is a failure of the mitral valve between the left ventricle and the left atrium. And that is extremely serious because that is what drives the blood to your body, oxygenated blood to your body. So that can have severe consequence. This is, never mind. This is just to show you the coronary vessels again, to remind you of the current situation of the coronary vessels. And the blockage of those coronary arteries is consequential because it means that heart muscle itself is being deprived of oxygenated blood. Now, those vessels may be narrowed and still allow blood to pass through. And this can mask the fact that those vessels are actually damaged or diseased. And very often people don't know that their coronary arteries are in fact narrowing because they aren't that narrow that they start to feel effects. But some people actually, the vessels either temporarily close or they narrow to such an extent that when the heart is placed under any stress, the blood flow becomes impeded to heart muscle and they begin to get agonizing pain in the heart muscle, which passes off if they can widen the blood vessels. This is a condition called angina pectoris. And what people with angina do is, if they have this pain, they will take a substance like nitroglycerin, which causes blood vessels to dilate. And that will relieve the pain. It does not relieve the disease. It doesn't take the disease away, it just relieves the symptoms. In situations where that vessel becomes severely narrowed, the real danger is it will slow down blood flow enough that platelets will begin to settle, and they will cause a blood clot to form. A blood clot inside a vessel is called a thrombosis. And when that occurs in a coronary vessel and the vessel becomes blocked entirely, downstream of the vessel, the heart muscle is completely deprived of oxygen, and the heart muscle itself will begin to be damaged and ultimately to die. And this can be so severe that the whole functioning of the heart becomes impacted. This is what we call a myocardial infarction. It's where the myocardium, the muscles of the heart, become deprived of oxygen because of blockage of the vessel. And it's an extremely dangerous situation. And it can lead to total heart failure. That is the inability of the heart to pump blood to the body, and consequently to death. This term heart failure can also refer really to a more chronic situation where the heart is simply is becoming so impaired that it is unable to operate efficiently. You can have heart disease in any part of the heart, in either of the atria or in ventricles. And the symptoms of a heart failure, of impaired heart function in heart failure, depends on which part of the heart is actually affected. Most commonly, we see a condition called congestive heart failure. And this is where there is a failure of the left ventricle to pump blood to the rest of the heart. And as a result, blood pressure begins to build up in the lungs, in that circulatory system to the lungs. And because of the increase in pressure in the vessel, serum begins to leak out through the blood vessel walls and fill the lungs. And this is where the congestive part of the name comes from. And that in itself is an extremely dangerous situation. Then there are a whole slew of these beat irregularities. And the one that I do want to emphasize is this one here, which is ventricular fibrillation. I emphasize this because not frequently, but with regularity, we'll hear especially about young people who suddenly collapse, like on a basketball court or something, with heart failure. The heart suddenly goes into the system of ventricular fibrillation. The control of the pacemaker is lost, and instead the ventricles just start twitching in a chaotic manner, which cannot deliver blood to the rest of the body. Very often the person will just simply drop instantaneously in unconsciousness because their brain is being deprived of oxygen. This is the reason, if you go to St. Francis basketball court, for example, and several places in the college, you will see on the wall there is a defibrillation machine. And what a defibrillation machine is used for is that it sends a sudden, very brief, very strong electrical pulse into the pacemakers of the heart, and it resets them. It gets them, hopefully, to start firing again in a coordinated fashion so that the ventricles again start to contract properly. So it's a good idea, if you're a sportsman especially, to find out how those defibrillators work. There are a slew of infectious diseases of the heart as well. Pericarditis is an inflammation of the pericardium. Myocarditis is any inflammatory condition of the muscles of the heart. It can be due to infections. It can be to toxins from an infection. And there can be unknown causes for it as well. Endocarditis, that is an extremely dangerous condition, and I mentioned it a little while ago in connection with COVID-19. Endocarditis is inflammation of the lining of the heart itself. This disease here, rheumatic heart disease, is the direct result of an infection, and by an infection by a very common bacterium, Streptococcus. We've all probably had strep throat, but you may not know that the Streptococcus, the bacterium that causes strep throat, can actually go on to cause some very serious diseases, in particular because it releases toxins into the bloodstream, and it itself may enter into circulation. And one of the effects of this is that it can damage the heart valves, especially in children. They usually have, first of all, a generalized illness, infection by Streptococcus, causing a disease called scarlet fever. And this very frequently will lead to the damage of, I'm sorry, not scarlet fever, a rheumatic fever. And this very often will lead to damage to the heart valves. This is now very uncommon. You seldom see this in children anymore because the underlying Streptococcus infection is so easily treated with antibiotics. Nonetheless, it does still occur. It would be especially of interest in developing countries, for example, where they may not have adequate medical care. Okay, so at the end of this chapter, please look and do the labeling exercise on the heart structures. And then there is a matching question that follows that. So please do that. And there's a 1% extra credit for you. I have not talked about heart surgery, but there is a section in your textbook on heart surgery. So read that, summarize that, pull in some information from other places, maybe from Wikipedia or whatever, to plump it up a bit, 2 pages, and submit to me by November 15th. That is for 1% extra credit. Okay, and with that, I'll say goodbye and see you at our next class. Don't forget, please, you have a test on Friday, and that I have put up study guides for both parts of that. It's special senses, and what else? Blood. So it's special senses and blood, and there are study guides up for you to follow.